Welcome to the webinar on eMTCoSim. This is ETAP's new solution for co-simulating the phasor domain along with the electromagnetic transient domain. In this presentation, we will cover topics such as when and why you would need this type of solution and demonstrate its use through a few case studies. My name is Fabian Uriarte and I will guide you through the rest of this presentation. Today, I will start with what CoSimulation is, the foundation from which eMTCoSim stems from. Then I will motivate two of ETAP's new products, eMTP and eMTCoSim. These are two separate products available starting with ETAP 20. Although they are separate products, they can work together. Then I will motivate these products and explain why and when you should use them. Finally, I will justify these products by running you through several case studies. Each case study highlights different benefits of using ETAP eMTP and ETAP eMTCoSim. The case studies span three scenarios. These are the co-simulation of a solar farm, energy storage, and a microgrid. So what is co-simulation? Co-simulation is the cooperative simulation of a system model by using different software packages. Doing so allows to span more physical domains by accounting for the contributions of other physical spaces that are normally not observable from the use of a single domain. We say that this is actually extending the capabilities of a software by coupling it to other more specialized software. The collective result will unarguably be the most accurate result because it presents the contributions from a multitude of specialized and mature engines instead of from one engine alone. For example, in this presentation we will show how to couple two different domains, the phasor domain and the electromagnetic domain. These two domains will be solved with different engines and fused together to produce a more credible and cohesive result. Now that co-simulation has been explained, let's focus on the new ETAP eMTP, which solves only the electromagnetic transient domain. Remember, co-simulation couples two or more domains together. Co-simulation will be discussed later. At this point, we're only introducing ETAP eMTP, one of the new products to debut in ETAP 20. ETAP eMTP. This product is new in ETAP 20. Traditionally, ETAP's main focus has been phasor and load flow type of solutions. For example, transient stability, time domain load flow, short circuit analysis, and so forth. But with ETAP eMTP, we introduce a new domain, the waveform level electromagnetic transient domain. This new domain is new to the ETAP lineup. With this product, we can solve problems in the electromagnetic transient domain. Other engines we have are useful for their domains. Please note, all of our engines are currently independent and run separately. They are not coupled. Now let me point out that in the current release, ETAP's eMTP is powered by PSCAD's fast, mature, widely used, and well-known eMTDC engine. The eMTDC engine is currently responsible for solving the electromagnetic transient domain for ETAP. So to recap so far, we have introduced the concept of co-simulation and ETAP's new product called ETAP eMTP. This new product, available starting with ETAP 20, is an electromagnetic transient engine. We also said that ETAP engines, including ETAP eMTP, are mostly independent, not coupled to one another, and specialized in a single electrical domain. Having said that, we can now introduce a new product, an orchestrator, an enabler, a coupler, a cross-cutter, eMTCoSim. This product is also new in ETAP 20. Its purpose is to co-simulate two electrical domains together. In this presentation, we will demonstrate how it can be used to co-simulate the phasor domain and the electromagnetic transient domains. We're going to take one of ETAP's phasor domain engines, namely the transient stability engine, and couple it with ETAP eMTP for a more credible and cohesive simulation result. So now let's talk about eMTCoSim. This solution, also new in ETAP 20, couples the phasor and electromagnetic transient domains. The phasor domain is currently used to simulate large networks. This is the typical use. The electromagnetic transient domain is used to obtain high fidelity results at smaller integration time steps. By co-simulating these two domains, one can have the larger networks in the phasor domain and the high fidelity networks, or portions of the networks, in the electromagnetic transient domain together in a single simulation run. If you take this chart, for example, the same chart now shows instantaneous waveforms for voltage and current, but we also show RMS phasors produced from a phasor engine. This is not the same as calculating the phasors from the instantaneous data using one engine. Now we're talking about two engines, not one. One engine for each domain. So let's talk about the phasor domain and the electromagnetic transient domain in more detail. A common question we get is, when and why should I use one versus the other? Perhaps the best way to explain the when and why is by explaining the pains and benefits of each domain. The benefits of a phasor domain are its ability to model large networks without sacrificing simulation speed. Also, you typically have access to a larger library of components because the data from manufactured data sheets is compatible with the data that phasor engines require. Another benefit is the analysis, which is easier in the phasor domain because we're mostly trained to validate phasor type results by hand. Similarly, plots are easier to inspect in the phasor domain. The pains or challenges of the phasor domain simulation are the accuracy. Since we use phasors, we miss out on transients, waveforms, harmonics, and even wave shape information such as non-periodic behavior. As you know, there is no way to know or reconstruct the wave shape that generated a fundamental phasor. And if you look at the control libraries, typically electromagnetic transient engines have more specific control blocks such as part transformations, phase lock loops, PWM signal generators, and so forth. Additionally, power electronic insight is not available in the phasor domain alone. The benefits of the electromagnetic domain are its accuracy. Since we use small integration time steps, the results are more accurate. The level of detail is also superb. Since we have visual access to waveform level results, we can see exact event times and the amplitude of non-repeating events such as spikes or dips. The electromagnetic domain also offers power electronics and control system insights. For example, one can use the electromagnetic transient domain simulation to develop PWM or fast-acting PID controllers. The pains of the electromagnetic transient simulation are typically its speed. Unless you use an advanced numerical technique such as power system partitioning, low failure sparsity, optimal solvers, network reductions, or multi-core transient simulation capabilities, an electromagnetic transient simulation is typically slow relative to the phasor domain. Therefore, the electromagnetic transient domain trades simulation speed for accuracy. Finally, parameter sets needed for electromagnetic transient simulations are hard to find. One typically requires snubber impedances, inductance, capacitance, and other hard to find parameters, in particular for control systems tied to electromagnetic transient simulations. So let's introduce eMTCoSim and what problems it solves. Now that we have explained the when and why to use the phasor domain and the electromagnetic transient domain, the benefits of eMTCoSim can be understood. This tool allows to co-simulate both domains while reaping the benefits of each and foregoing the pains of both. This is the gem of eMTCoSim. Additionally, co-simulating two domains fosters collaboration between separate teams. Now one team can focus on the phasor domain exclusively, while the other team can focus on the electromagnetic transient domain. When each team finishes, both models can be co-simulated using eMTCoSim. So in sum, eMTCoSim, new with ETAP 20, enables the co-simulation between the phasor domain and the electromagnetic transient domain. In ETAP, the electromagnetic transient domain is solved with the new ETAP eMTP. ETAP eMTP is not eMTCoSim. To demonstrate the benefits of eMTCoSim, we're going to show 3 case studies. The first will be a solar farm co-simulation to show that one can have a lot of detail down to the solar cell radiance and temperature levels. With this much detail, a standalone electromagnetic transient simulation would normally be slow. But with eMTCoSim, this problem goes away. Isn't that highly desirable? I would say so. The second case exemplifies a storage system which is not available from typical ETAP phasor domain libraries. Therefore, eMTCoSim can be said to extend ETAP libraries by allowing the use of elements available exclusive to the electromagnetic transient domain. This example also demonstrates plug and play, where different teams focused on different domains. Finally, the third case study will show that one can have a diverse generation portfolio with a lot of detail, supplying a large network modeled in the phasor domain. Then we disconnect the two domains and observe how the phasor angles on both sides of the disconnection start to diverge. This is interesting because the two networks are not connected, yet they are still being co-simulated and remain coupled at the numerical level. This allows seeing the relative phase angle difference across both domains. Truly powerful. By the way, I'm going to quickly mention how the data is converted between the two domains. The phasor domain produces phasors. This data is directly convertible to quantities that the electromagnetic transient domain can understand. However, on the way back, the electromagnetic transient data first runs through a signal processor. This can be thought of as the inverse or reverse transformation required to feed electromagnetic transient data into the phasor domain. This signal processor is proprietary and offers our best-in-class algorithms. This means that the electromagnetic transient domain data is classified and processed carefully before feeding it back to the phasor domain. We use the signal processor to calculate power flows and RMS sequence information. So now let's demonstrate some of these benefits by running through case studies. We said earlier that we have 3 case studies to show, so let me dive into each one a little more. The first case study will show that eMTCoSim allows to have detail without compromising performance. This case study is rich in power electronics and detail. The second case study will show how we can extend our ETAP library with custom models typically available to electromagnetic transient engines. This case study also illustrates how different teams can produce independent models and co-simulate them together. The third case study will show that we have a complicated active network of renewable sources on the electromagnetic transient domain and how they can feed power back into the phasor domain. Additionally, this case study proves that we can have long-running simulations even with small time steps, something otherwise challenging to traditional electromagnetic transient engines when they run alone. So now let's demonstrate some of these benefits by running through the case studies. Let's start with the first one. The purpose of study case 1 is to show that it is possible to have detail only when you need it. It also shows that the simulation speed does not need to be compromised when having such detail. Finally, it shows that the phasor and electromagnetic transient domains produce more meaningful charts than using a single domain alone. So let me show you some images before we jump into the simulation. On the phasor domain, we have a medium voltage network. On the electromagnetic transient domain, we have a 5 megawatt solar farm with solar cells, power electronics, and a lot of detail not otherwise possible when only using the phasor domain. The boundary block between the two domains is shown with a red circle on the phasor domain and with a blue block on the electromagnetic transient domain. The red circle and blue block mean the same. They represent the point of common coupling seen from each domain. Here we show a table of events where each row shows the times of each event and each column represents the different domains. So for example, at t equals 0, both domains start running their engines. By the way, eMTCoSim synchronizes the execution of both engines to keep them in lockstep throughout the simulation. There is nothing asynchronous here. At t equals 0.5, eMTCoSim starts exchanging data. We typically leave a little bit of time before the exchange begins, so each domain solver can settle. At 1.5 seconds, we have a fault on the phasor domain, which is cleared after 0.1 seconds. The fault is on the main bus, shown with the yellow lightning bolt. At 2.5 seconds, we have a single phase fault on the electromagnetic transient domain, which gets cleared in 3 cycles. We want to show that events on each domain propagate to the other side. And finally, the simulation ends at 3 seconds. Let's take a look. As a first example, we show example CoSim, which comes included with the ETAP installation. To get things started, we enter the Transient stability mode, then the CoSim submode. The next step is to define where the phasor and electromagnetic networks will interface. In this case, we selected a lump load as the point of interconnection. When that is done, we can open the Transient Stability Study Case Editor, specify simulation time, settings, and set up events as in a normal transient stability study. Additionally, we can confirm the boundary element is the load we just selected. The next step is to set up the electromagnetic side. We click the eMT button to launch the editor. In this case, we have already defined a 5 megawatt solar farm including subnetworks, inverter, boost converter, PowerPoint tracker, and other controls. This example contains 20 PV arrays of 250 kilowatts each. This example is publicly available, by the way. The example was chosen arbitrarily to show how a detailed electromagnetic model can easily be co-simulated with the phasor domain. When we are done with the electromagnetic transient domain, we close that editor. The eMTP engine will be reopened later. Now let's start the co-simulation. In ETAP, we click the Run Transient Stability button as normal. When we do this, ETAP automatically starts both domain engines and the co-simulation engine, which is used to synchronize the data exchanges between the two domains. On the left side, we see ETAP's Transient Stability Simulation, and on the right side, we see eMTP simulation. So we wait here a little bit for the first event. So here we go. At time equal 1.5 seconds, there is a three-phase fault in the phasor domain. The fault is felt on the electromagnetic transient domain, which causes the solar farm to trip and then to reconnect. The next event is a single-phase fault to ground on the electromagnetic transient domain at 2.5 seconds. Correspondingly, this fault is felt on the phasor domain as well. Both simulations continue to run and are stable throughout. When the simulation finishes, a CSV file will be written out. The CSV file contains boundary data. From the CSV data, the phasor quantities are shown on the left and the electromagnetic quantities shown on the right. We can also use the slider and the transient stability module in ETAP as normal to jump to events and look at network measurements. This is a normal feature in transient stability which can also be used for other simulations. On the electromagnetic side, we can use moving plots to gather understanding of events. All in all, both domains were co-simulated stably and to completion. Events on both sides were staged and sensed by each program. Remember, we had a lot of detail on the electromagnetic transient side, which would have been painful to simulate if we would have added the burden of the phasor domain network to the same engine. That was nice. We had both detail on one domain and a large network on the other. eMTCoSim gave us the best of both domains and overcame the pains of each. The pains went away. This is fabulous. What we are showing here are quantities produced from each domain. The left column shows quantities produced by the phasor domain. The right side shows instantaneous data and RMS data overlaid. On the bottom right, we show power flows to the point of interconnection. Although ETAP produced charts for each domain, we also include Python scripts to produce more customizable plots as the one shown here. To keep the presentation to a reasonable length, we will move on to the next case study and omit describing the electrical responses, which should be well understood. You can always request a demonstration of eMTCoSim by contacting sales. So let's talk about case study 2. The second case study shows how eMTCoSim solves some of the pain points mentioned earlier. In this case, we can simulate a custom energy storage while keeping the details. Custom system models are typically not available in Phasor domain libraries. Therefore, eMTCoSim allows extending libraries by allowing custom models, even if the custom models are in a different domain. It should be noted that we have no limitation on power direction. That is, power can flow forward and backwards through a domain boundary. This also means that we can have active and passive networks on either domain. Finally, this case study shows that a model can be developed by two teams. For instance, the energy storage system can be developed by a research team, while the Phasor domain can be provided by, say, a team focusing on the utility side of things. These two models can be co-simulated without having to recreate either one. So in case 2, we have a similar network on the Phasor domain. The boundary is shown by the red circle. This is where the Phasor and electromagnetic transient domains interface. On the electromagnetic transient domain, we have a highly specialized energy storage system that can absorb and inject power into the Phasor domain. The blue block on the electromagnetic transient domain is the point of common coupling, corresponding to the red circle on the Phasor domain. To stage some events, at 1.1 we have a 3-phase fault on the Phasor domain. The fault is cleared at 1.2 seconds. And finally, the simulation stops at 2 seconds. Please pay attention to how fast the simulation runs, despite there being several power electronic converters and control systems in the storage system. Additionally, these two independent networks were created by separate teams. eMTCoSim stitches these two models together and enables a co-simulation between them. There was no need to recreate either model in the other domain. To get started, we enter the transient stability mode, then the CoSim submode on the same TS toolbar. The next step is to mark a lump load in ETAP as the interface point. In this case, we marked a lump load as the point of interconnection. Users can specify events and simulation time settings in the study case editor and also confirm that the CoSim element selection from the CoSim page is correct. The next step is to set up the electromagnetic transient domain using ETAP eMTP. We click to launch the eMTP editor. In this case, we have already defined an energy storage converter which is modeled with a rectifier. The converter is enabled at 0.3 seconds and includes 2 sets of controllers, one to maintain DC voltage and another one to charge and discharge the inductor. Reactive power control can also be set up by means of a PI controller. Now let's start the CoSimulation. We have to close the eMTP domain first. We go back to ETAP and click the Run Transient Stability button as normal. When we do this, ETAP automatically starts both engines and the eMTCoSim engine, which is used to exchange data between the two separate domains. At this time, both engines are running together and exchanging data. As we can see, there's an event at 1.2 seconds, which is a 3-phase fault on the Phasor domain. The fault is reflected on the electromagnetic transient domain as expected and clear after 100 milliseconds. The co-simulation speed is fast, but also depends on the model complexity placed on the electromagnetic transient domain. When the simulation finishes, a CSV file is written out and is plotted using a Python script, which is included in this co-simulation package. Important ETAP quantities are shown on the left, while the remaining PS quantities are shown on the right. Similar to this study, multiple types of studies could be performed with ETAP eMTCoSim. For example, an electric arc furnace, TRV, and so on. That was fast! We showed a detailed energy storage system could be co-simulated with a large network in the Phasor domain. Also, the models in each domain were provided by separate teams. By simply defining the boundary point on each domain, it was possible to have interactive bidirectional flows in the two domains. This is co-simulation by definition. We have here the results from two domains. We see the Phasor domain voltage on the top left charts dropped abruptly during the fault. We can also see how instantaneous currents behave before and after eMTCoSim begins the data exchanges at 0.5. This level of detail is not possible in the Phasor domain alone. And if we look at the powers on the bottom right, these powers were produced by converting the instantaneous voltages and currents using our signal processor. There is no power flow before 0.5 seconds because we declared this time as the beginning of the CoSimulation, which allows for both engines to settle. Prior to this time, the networks advance in time quasi-independently. For a private demonstration on eMTCoSim, you can always reach out to ETAP cells. So let's now talk about case study 3. Finally, the third case study will show that one can have a diverse generation portfolio with a lot of detail serving a large network modeled in the Phasor domain. As shown before, there is no need to model large networks in the electromagnetic transient domain when you have the Phasor domain to handle that for you. Another benefit of eMTCoSim, which at times is implied, is that we can have long-running simulations at small time steps, such as 10 to 15 microseconds, yet still be able to simulate through 10 seconds of runtime data. With the traditional electromagnetic transient engine, this will be computationally expensive due to the large amounts of data that would be generated. But with eMTCoSim, much of the unnecessary data is abstracted away and can be captured in Phasor form instead. So similar to as explained before, we have a mixed portfolio of sources on the electromagnetic transient domain. On the Phasor domain, we have a mixed network including AC and DC subnetworks. This is a long-running simulation where the time step is 15 microseconds. And we have an event table showing the events for this case study. At 6 seconds, we stage a 3-phase fault. We're indicated with the yellow lightning bolt. At 6.2, the fault is cleared. Notice the concept of simulation start versus CoSimulation start. Both engines start at t equals 0. However, the data exchanges that couple them start after 1 second of simulation. The third example has a microgrid system modeled on the electromagnetic transient domain side. The Phasor domain, similar to the other examples, is based on ETAP's example ANSI project. To get things started, we enter the transient stability mode as normal. Then we can open the transient stability study case editor and specify simulation time settings and events. Additionally, we can confirm that the boundary element is selected correctly. We need to make sure that the CoSim mode is activated. Now, we open the Electromagnetic Transients project to examine the microgrid. The microgrid consists of a wind turbine, a solar farm or battery storage system, a diesel generator, detailed models of cables and lines, and so on. The diesel generator has speed governor control, which reduces the diesel generation when islanding happens. For the wind generator, a Type 3 model is used. As mentioned, a PV system is also used in this example. The microgrid model is publicly available and can be downloaded as well. A battery storage is also included to support the PV system for which a detailed model is used. The breaker seen at the top here will later separate the Phasor and electromagnetic transient domains. As it can be seen, this breaker will be open at time equals 6. The 2 meters are used on both sides of the breaker for examining the angle separation. The meters will measure the voltage angle on the microgrid side. And here we have some more plots, and we will get back to them later during the CoSimulation. Now we close the electromagnetic transient domain program and run the CoSimulation by clicking the Run TS button. At this point, eMTCoSim automatically launches the eMTP engine. Now we can see the 2 programs running together. Live plots update the signals as the simulation advances on both domains. One may zoom in during or after the CoSimulation to get additional insight. Similarly, the results can be viewed in the eMTP side during runtime. At time equals 6, there is a fault, a 3-phase fault at bus sub 2A on the Phasor domain side. This causes the microgrid to separate from the Phasor domain and become islanded for the rest of the CoSimulation. After this event, and due to the breaker action, both electrical networks become independent. No data is exchanged between them anymore. As can be seen from the figures on the right side, before time equals 6, the voltage angles on both sides of the breaker are almost identical. However, after the two subsystems separate, the phase on both sides of the breaker diverge permanently. As a result, we cannot reconnect the two systems without a synchronization mechanism, which is not part of this case study. At the end of the simulation, a Python plot is shown. On the left column, we see boundary bus, voltage, angle, and frequencies. On the right side, we see boundary electromagnetic transient quantities such as instantaneous voltages and currents. At the synchronization time, which is at t equal 1 second in the simulation, slight changes are noticed as a result of closing the data exchange loop. This is the expected behavior. All right, let's wrap up this presentation with a summary of what was said today. ETAP eMTP is a new product in the ETAP 20 lineup. eMTP enables electromagnetic transient simulation in ETAP. This was not possible in previous releases. eMTCoSim is also new. This product is different than ETAP eMTP. This product is meant to bring together two domains, the Phasor domain and the electromagnetic transient domain. This new product reaps the modeling benefits of each domain and also removes their pains by addressing them outside of the domain boundary. We showed a few case studies to demonstrate how you can have highly detailed network models in eMTP without compromising simulation speed. We also showed that power can flow through the boundary and that events on any domain propagate to the other. We encourage the use of teams to make each model and let eMTCoSim stitch the models together for you. And finally, in ETAP 20, you can have high fidelity, waveform level detail only where you need it. This is new and now possible with eMTCoSim. Thanks for your attention.